Even though pre-trained models excel at computer vision tasks for object classes that they had been trained on, they are unable to recognize objects that belong to other classes. If faced with the necessity of training a model for new object classes, one could pursue two options. The first would be to take a state-of-the-art convolutional neural network architecture, such as ResNet, to randomly initialize the model parameters, and then to train the model from scratch on labeled data for the new object classes, just as it had originally been trained for existing classes. The drawback of this approach is that because state-of-the-art CNN architectures are complex and have a lot of parameters, one would need a huge dataset to train all of these parameters, and it would be a computationally intensive task requiring a lot of time and computing resources. The second approach is to start with a pre-trained model to freeze the weights for all of the CNN's layers except the last one, or perhaps the last few, and to retrain only the weights for these layers. Because there are a lot fewer weights that need to be trained in this case, the training dataset could be much smaller, and the training wouldn't be as computationally expensive. But why could this approach be expected to work? Remember, the early layers in a CNN detect very basic patterns, such as line segments, that are then combined to more complex patterns by subsequent layers. Let's say we have a CNN that has been trained to recognize various animals: dogs, cats, bears, donkeys, kangaroos, etc. Imagine that we wanted to retrain the CNN to recognize a new type of animal, such as a rabbit. A rabbit has many features that are similar to other animals. Its eyes might look like a cat's, its ears like a donkey's, and its hind legs like a kangaroo's. Our CNN may be already adept at recognizing all of these parts and just needs to be trained to combine them in new ways. But that is precisely the task that the final layers are responsible for. So only the weights for these layers need to be retrained. That is the basic idea behind transfer learning. Often, CNNs can be retrained to recognize new object categories using very small datasets. Using transfer learning to retrain only a small subset of a neural network's parameters is one of the reasons for that. A second reason is that a single image in a dataset can be used to generate multiple other images that can be used for training using various transformations. Take the original image of a yellow lab. If we take its mirror image, it can be used to teach a neural network that a dog facing in a different direction is still a dog. If we crop out different parts of it, the network can learn to recognize a dog based on just some of its parts. If we rotate or distort the image, the network can learn to recognize dogs from different angles. If we vary the intensities of different color channels, the network can learn to recognize dogs under different lighting conditions. In effect, each of these images serves as a separate training sample. That is the idea behind data augmentation. That is commonly used in conjunction with transfer learning. A small image dataset might be collected, enlarged using various transformations of the images, and then used to retrain a neural network for new object classes. Let's look at an example of how to perform transfer learning in practice. We will train a CNN to perform image classification for two categories that it isn't familiar with: bees and ants. The dataset we use will consist of 124 training images of ants and 121 training images of bees. It also includes 70 test images of ants and 83 of bees. When we load this dataset, we will rely on its directory structure for creating the training and test data loaders and the labels for the images. The directory structure that we will use is shown on the slide. The dataset is stored in the directory Hymenoptera data that has two subdirectories: train, containing all the training data, and test, containing all the test data. The train and test subdirectories each have a subdirectory for every class that we will be training the CNN for. In this case, an ANTs and a bees subdirectory. The names of these subdirectories will be used as the labels for the new classes. Inside these subdirectories will be image files showing ants and bees respectively. The file names for the images themselves are of no consequence. As usual, we start by loading the data and pre-processing it using Torch Vision transforms. For the training data, we perform data augmentation using random sized crop and random horizontal flip. Whereas for the test data, we do not perform augmentation, but simply a center crop, removing pixels at the boundaries of the image so as to focus on its central part that presumably contains the object of interest. For both training and test data, the images are then converted to PyTorch tensors, and the pixel intensities are normalized. The training and test datasets are then wrapped into data loaders objects. The dataset sizes and class names are extracted and stored. Training large models is most efficient on GPUs that allow for massively parallel computation. Therefore, we check whether a GPU is available for training, and if so, tell PyTorch to send the model to train on it, and otherwise use the CPU. For our model, we start with a pre-trained ResNet 18, a smaller version of the ResNet architecture than ResNet 50, one of the CNNs that we used in the previous lesson. We iterate over all parameters for this model and freeze them by setting the required _grad attribute for each of the parameters to false. We then reinitiate, that is, redefine the final layer of the model, the fully connected layer that is called FC. We defined it as a fully connected layer, nn.linear, that takes the same number of inputs as it did in the ResNet 18 architecture originally, but has only two outputs, corresponding to the two classes, ants and bees, for which we plan to train the model. A newly created layer in PyTorch has the requires _grad parameter that defines whether its parameters will be adjusted during training set to true by default. Therefore, we now have a ResNet 18 model with a modified output layer for which all parameters, except for those of the fully connected output layer, have been frozen. Because we are solving a classification problem, we will use cross entropy as our loss function. We will be using the stochastic gradient descent optimizer to train the model's parameters, just like for the custom CNN that we built for recognizing handwritten digits in the second lesson of this course. Because we have frozen all parameters in the model, except for those of the output layer, only the parameters for that layer will be trained. We set the initial learning rate to 0.001 and the momentum for SGD to 0.9. We also schedule the learning rate to decay by a factor of 0.1 every 7 epochs, so that as we make finer adjustments in the later training stages, when we get closer to the optimum model parameters. We train the model for 25 epochs, assessing its accuracy for the test data after every epoch. When training the model, we set it to training mode using the train method, and when checking its accuracy for the test set, we set it to evaluation mode using the eval method of the nn.module class. This tells PyTorch to perform forward propagation prediction, then back propagation parameter adjustment for the training mode, but only forward propagation for evaluation mode. For each training step, we keep track of the loss and the prediction accuracy, and we adjust the learning rate as scheduled. If the model accuracy for the test set after any epoch is the best one seen yet, then the model parameters after that epoch are saved as the best model. The best model accuracy that we achieve over the course of 25 epochs is over 96%. Here we can see the predicted labels for a few test images. All of these labels are correct. Our model achieves over 96% classification accuracy despite having been trained on fewer than 250 images. That is the power of reinforcement learning and data augmentation. For many computer vision applications, it is more practical to use reinforcement learning to retrain a state of the art pre trained model for new object classes of interest than to develop your own model architecture or to train a state of the art model architecture from scratch, starting with randomly initialized parameters.